Okay, you guys, so we're going to finish this section, this last section for chapter 9. This is kind of bringing everything together now that you've learned for all of chapter 9. This is one of the most important sections for the exam, because if you can do chapter 9.8, you can pretty much do a lot of the stuff that came before. So I'm planning on putting quite a few questions from chapter 9.8 on the exam. So this is probably the most important section to study. So just make sure you go over this, ask me questions about it, shoot me emails. But just make sure that you understand what's going on with 9.8. So in this section, it's called Exponential and Logarithmic Equations and Problem Solving. So one of the main reasons we're learning all of this information about exponential functions and logarithmic equations and functions is so we can use these to solve problems, okay? So the first thing we're going to talk about is solving exponential equations. Then we're going to do logarithmic equations. Then we're going to solve problems that can be modeled by exponential and logarithmic equations. Okay. So here's a very, very important property. Okay. So you should have a list of quite a few properties of logarithms currently, where it says, and this is just another one that we're going to now add. It says, let A and B and C be real numbers such that log base B of A and log base B of C are real numbers and B is not 1, so not a base of 1, then the following is true, or these are equivalent. Log base B of A equals log base B of C. If that's true, that is equivalent to saying A equals to C. So what this is saying is that if you have two bases that are the same of two logarithms and they are equal to each other, then their arguments must also be equal. So this A has to equal C, and that's what we say right here. Okay, so once again, you are assuming that this is a true statement. And if this is in fact something that you are saying is true, you're saying is true, then this is also true. But it could go the other way as well. You could say like M equals N. Well, then that means that log of M equals log base 10 of N. Okay. So it can go either way. You can start with this and end up with this, or you could start with, or you could start with A equals to C and end up with log base B of A is equal to log base B of C. It just really depends on what you're working on for that problem. Okay. So let's take an example of this on this first one. Okay. So it says solve 4 to the x is equal to 7 and give the exact solution and also give the 4 decimal approximation. Okay. So here's the thing. Normally, when we have 4x equals 7, we would try to make the bases the same. And then remember, like if it was 2 to the x is equal to, or 2 to the 3x is equal to, I'm going to do this better. 2 to the 3x is equal to 32. Well, we know that we could rewrite this as 2 to the 5th, right? Because 32 is 2 to the 5th. And then we could say, oh, well, then 3x equals 5. So then x equals 5/3. And that's how we solved it in the exponential section. I think it was back in 9.3, maybe 9.4. Okay. So now here's the thing. That worked because I was able to take 32 and rewrite it as 2 to the 5th. And now these have the same basis, right? We have 2 to the 3x and 2 to the 5th. So that works as long as you have same bases, okay? The problem here is that I can't take a base of 4 and turn it into a 7 exactly, or vice versa. So what I'm going to do is I'm going to use this property here that says that log base B of A equals log base B of C means A equals C, okay? But I'm going to go backwards. I'm going to say, what if I were to find the log of this and the log of this? So I would now have log base 10 of 4 to the x equals log base 10 of 7. And remember, it says base B right here, but I'm just going to use base 10 because if I need to do a decimal approximation, I have base 10 on my calculator. I could have just as easily have done this as well, guys. I could have done natural log of 4 to the x equals natural log of 7. Both would give me the same answer, and I'll show you that in a second. So now we have the log of both of them, right? And remember, there's a property of logs that says I can take the exponent and move it to the front of the argument. So this will become x log base 10 of 4 is equal to log base 10 of 7. Now I divide both sides by log base 10 of 4, log base 10 of 4. So I have x equals log base 10 of 7 divided by log base 10 of 4, right? So what we do is on our calculator now, we do log base 10 of 7 divided by log base 10 of 4. And we get 1.4037 if we round off. So let's do that. So this is approximately 1.4037. Let me double check and make sure that's what I got. They said round to 4 decimal places. Yeah, 1.4036, and then it will be 7. Okay. Sounds good. All right. Now let's do it with natural log just to make sure. So once again, this is the exact answer, log base 10 of 7 divided by log base 10 of 4. And this is the decimal approximation. Okay. Now let's do this one. Once again, we're going to move the power to the front. So this is the natural log of 4 equals the natural log of 7. Divide both sides by the natural log of 4, divide by the natural log of 4. So we have x equals natural log of 7 divided by natural log of 4. So this is the exact answer, right? And then we can have a decimal approximation. We'll do natural log of 7, enter, divided by natural log of 4, enter, and we get 1.40367. So once again, the same answer, 1.40367. So I'm going to round that to 7. Okay, so once again, we have our decimal and our exact. This is the exact. This is the decimal approximation. Okay. So this is what you do when you are unable to get, when you're asked to solve and you cannot make same bases, to use your little trick with exponents or your little property with exponents. So let's move on. Hopefully that's and this is a very strong test question. This is like a very straightforward test question. Okay. By using the definition of logarithms in terms of exponents and properties of logs, we can solve logarithmic equations. So now we can go the other way. Okay, so now if we choose to, we can use the swirly to solve a logarithm. So we can go the other way. So this becomes 4 cubed equals 8x minus 6. Oops. 8x minus 6. But we know 4 cubed is really 64 equals 8x minus 6 plus 6 plus 6. So we get 70 equals 8x. Divide both sides by 8. And we are left with x equals 70 over 8. Or, cleaned up, they both have a 2, so we could divide both of these by 2. This would be 35 over 4. Okay, so that's what x equals, is 35 over 4. Okay, and then you can take and make sure that this value, when you plug it in, you get a positive number. Well, 8 times 35 over 4 would be, what would that be? 70. Oh, hold on. That would be 2 times 35, which would be 70. Minus 6 would be 64, and 4 cubed is 64. So if I wanted to check this, I could just do log base 4 of 8 times 35 over 4 minus 6 better equal 3. Okay, so this will be log base 4, and this would be 70 minus 6 equals 3. So log base 4 of 64. And again, I'm getting fancy, right now I already know this is the correct answer, but I could then say this is log base 4 of 4 cubed equals 3, move the power to the front. This becomes 1, and we have 3 equals to 3, which checks out. I already knew it was going to work the moment I plugged it in like that, but I was just showing you guys what I was thinking of. Okay, so again, this is just the check. You don't actually have to do this. But this is how you know you have the right answer. Okay. Remember, with logarithms, when you're solving, you normally want to verify that you will get a positive number when you plug it in. Okay. Now, this one is definitely a test question, right? This is going to be on the exam for sure. Okay, as will, this one. This is also a test type question. Okay, so these are really good questions to study. Make sure you know how to do those. If you're not sure how it works, come talk to me during our meeting times and I'll help you out. So now this one, we're going to use properties of logarithms to help us. Okay, so we see that we have two logs with the same base and they're being added. So there's a property that says I can do log base 6 of x times x minus 1, right? Remember, when you have a addition of two same bases of logarithm or two logarithms with the same base, you can multiply their arguments. So this would become log base 6 of x squared minus x equals 1. Okay, now we know that when we want to solve a logarithm for x, we can undo it and rewrite, or not undo it, but we can rewrite it as its exponent. So this becomes 6 to the 1 equals x squared minus x. Okay, and then this will now become 0 equals x squared minus x minus 6. Okay, let's see here, let's factor this. So x minus 3 times x minus 2, oh, plus 2, sorry about that, equals 0. Up here now. So that's factoring, let's see, negative 6. Let's just make sure that's right. X minus 3, x plus 2. Yep, sounds good. So then we have x minus 3 equals 0 and x plus 2 equals 0. So x equals 3 and x equals negative 2. Now we have to verify that both of these answers are acceptable in the domain of the original logarithms. So if I take 3 and I plug it into here or here, will I get positive numbers? So let's see, if I plug 3 into this one, I'll get a positive, and I plug 3 into this one, I'll get a 3 minus 1, which is positive 2. So this is okay. So I like this number. However, when I take negative 2 and I put it in here, it's broken, and it also breaks in there. In both of the logarithms, again, it only has to not work in one of the logs or be a domain issue in one of the logs, but it turns out in both of them, negative 2 would cause a domain issue, okay? So negative 2 is not an answer. So our only true answer is x equals 3, and we threw out negative 2. It is not a valid solution for this. Okay, so this is a test question. Okay, so this is a really good test question. This is something you are for sure going to see on the exam. And there's good practice in the homework as well on these. Okay, now why don't you guys pause the video and try this one real quick. Okay, so hopefully you guys are unpaused now. So when you see the minus sign means division between the arguments. So what I'm going to do is I'm going to do log base 4 of 10 divided by x equals 2. Remember, we want to rewrite multiple logarithms as one log, so then I can rewrite them as their exponential form. So I'm going to do 4 to the 2 is equal to 10 over x. So this is going to be 4 squared is equal to 10 over x. Remember, that's what a logarithm says, is that the base to this power will, or to that exponent, will give me 10 over x. Okay, so now this means that this is 16 equals 10 over x. We can turn this into x over 10 equals 1 over 16. And then we cross multiply. You know what? I guess we could have cross multiplied from the beginning. We could have just done this. Oops. We could have just said (16 times x has to equal 10 times 1. So let's do that. 16 times x has to equal 10 times 1. So then divide both sides by 16. So then we have x equals 10 over 16, which we know is 5 over 8. And then if we plug that answer in, we get a positive in here. So we're okay with that, so it doesn't cause any domain issues. So our answer is 5/8, and we're okay with it, okay? So this is, again, really good practice problems. For these, you definitely want to know how to do problems like this. They can get a little bit worse than this. Make sure you know how to do the style where you end up having to factor. Definitely a test type question. So just let me know if you have any questions about the homework or anything like that. All right, so population size y of a community of lemmings varies according to the relationship y equals y naught e to the 0.15 t. In this formula, t is the time in months and y naught, or y sub 0, is the initial population at the time 0. So this is our initial population. Okay, estimate the population after 8 months if there were originally 2,000 lemmings. So what I'm going to do is I'm going to write down the formula. Y equals y sub 0 e to the 0.15 t. So they're giving us this formula, and they're telling us that the population size y of a community of lemmings varies according to this relationship. So they're telling us this is the formula that can allow us to determine how many lemmings there are. Okay, so they gave us the formula, and now it's our job to plug in what we know. All right, so we know that y sub 0 is 2,000 because they said originally there was 2,000. So we're going to say y equals 2,000. Then it says e to the 0.15. Now they said t is measured in terms of months from the original time equals 0. So we now have 8 months. So this is going to be times 8. Okay, so we have y sub 0 equals, now I'm not going to use the screen calculator. This one I think you guys can just do on your own. So this is 2,000 times second function e to the power of 0.15 times 8. And I get approximately 664023.23. Now they want 4 decimal places. So let's go 2338. They didn't tell us 4 decimals, but it seems like in multiple of the other questions, they've asked for 4 decimals. So I'm going to give them 4 decimals again. Okay, so we're going to say in 8 months, the population will be approximately 6,640 lemmings. Okay. So we found out that if you start with 2,000 lemmings originally, in 8 months, you will end up with 6,640. That's quite a bit. So they triple, according to this model, they triple in about 8 months, a little over triple actually, right? Like maybe not quite 3.5 times, 3.25 times the population in about 8 months. Okay, so they grow very rapidly, as you can tell. But they also did have a pretty large 2,000 starting population when we decided to start measuring. Okay, so let's see here. Let's go on to this next one. So how long does it take an investment of $5,000 to double if it were invested at 4% compounded quarterly? So here's our compound interest formula once again. A equals principal times the quantity 1 plus the rate divided by the number of times compounded, all to the power of the number of times compounded times time, the number of years. Okay, so this problem looks really bad, right? But it's really not that bad, okay? So first things first, let's start down here, okay? So let's write out what we know, okay? So they said, how long does it take an investment of 5,000 to double? Okay, well, what's double 5,000? That's 10,000. So that's where this number 10,000 came from. They're already doubling it. Now, something you'll notice, and they plugged in the rate of 0.04, and then they have 4 times t because it's compounded quarterly. So we see right here, compounded quarterly means 4 times per year. Okay, so that's where this 4 is coming from right here. This 4 and this 4 are from the number of compounds. That's our n, right? That's right here. Oops. That's our n, and that's our n. That's the number of times compounded per year. Okay. Now, what they don't know is how many years. So this is what makes this problem a little bit different. Okay. We haven't had to solve for a variable up here in these word problems before, but now we can because we have our exponential and logarithmic properties that allow us to work with exponents and logarithms, or convert to exponents from logarithms, or vice versa. Okay, so first thing we do is we divide by 5,000. So we end up with 2 is equal to 1 plus 0.04 over 4, all to the 4t. Now, once again, hopefully you guys notice it is not a coincidence. It is not a coincidence that I have a 2 here. Remember, they said, how long does it take to double? So if you're doing doubling time, this number will always end up being a 2. If you were doing tripling time, this number would end up being a 3. What if you were doing half-life? This number will end up being 1/2, right? So just keep that in mind. They're kind of telling you the what you're going to end up with when you do this little division that I did right here, okay? So now the problem is I don't know how to solve for this t up here. I mean, it looks really hard. So think about this real quick. What do you do when you have a variable in the exponent and you need to bring it down to the level playing field? Okay, think about that. We use a property of logs from way back up here. Well, we're going to use this property up here. Okay, so notice there's no logarithm here, and now I brought logarithms into the problem. Now, the only way I can bring this 4t to the front is if I was working with logarithms, but I currently don't see any logarithms. Remember, the property says we can just do this. Log, I'll do natural log. I like using natural log better. I'm going to say the natural log of 2 equals the natural log of, oops, I wanted to write it in red just for that, of 2 equals the natural log of 1 plus 0.04 over 4 to the 4t. Now I can move the 4t to the front because now I'm working with a logarithm, okay? So we're going to have the natural log of 2 equals 4t natural log of 1 plus 0.04 divided by 4, okay? Now, the natural log of 1 plus 0.04 divided by 4, we can come over here, we can say the natural log, you know what, let's do this first. Let's do 0.04 divided by 4 plus 1. So we actually have 1.01. So we can do this. Natural log of 2 equals 4t times the natural log of 1.01, right? If I clean this up a little bit right here. Now, remember, I'm trying to solve for t. So what I'm going to do is I'm going to divide 4 natural log of 1.01. This will cancel with this and this. These become 1, right? But whatever I do to one side, I got to do to the other. So we have 4 natural log of 1.01, okay? So now we have t equals natural log of 2 divided by 4 natural log of 1.01. So this is the correct answer, okay? So, but if somebody asks you, hey, how long is it going to take for your money to double? And you say, oh, natural log of 2 divided by 4 natural log of 1.01. That doesn't really help. So we want to know the actual number of years with a, you know, some level of approximation. So I'm just going to take the natural log of 2, hit enter, and then I'm going to divide that by 4. You know what? Let me do parentheses. Divided by 4 natural log of 1.01. Let's do double parentheses on that and close it. And I get 17.4152. So t is approximately 17.4152 years. Okay. So it takes a little bit more than 17 years for the money to double in value. Okay. So you started off with 5,000, and under these conditions with this interest rate and this level of compounding 4 times per year, it'll take you 17 years for your $5,000 to turn into $10,000. Okay. So this is a very classic doubling time problem, very normal, just a regular old problem you'll see in a class like this. So please make sure you know how to do this. I would not consider this a hard problem, but it also is definitely not an easy one. This is right in the middle of the road for this section. Okay. So that's going to do it for this video, guys. Let me know if you have any questions. If you need more practice or you need more help, you know, bring some homework questions to me during the meeting times, and I will see you then. Thanks for watching, you guys.